Okay, 1.3, properties of graphs of functions. Okay, so a lot of this is going to be a review. So let's review intercepts. When we, what is an x-intercept? Let's start there. The x-intercepts of a graph f, if there are any, are the solutions of the equation f at x equals 0. Okay, so to find this, you sub in y equals 0 and then you solve for x. The coordinates will be presented as some number x, comma 0. Okay, I want to speak to this though, like on this graph in example 1, just because it's there and it's handy. So for the x-intercept, this f at x, another way of writing that is y, obviously y equals 0. So the height value y is 0, right? 1, 0, negative 1. So that means anything that lies on this x-axis has a height of 0. And that's why it's in the form x comma 0. It's essentially how many units away from the y-axis it is, right? How many units away. Okay, then we have y-intercepts. So if x equals 0 is in the domain of the function y equals f at x, then the y-intercept of the graph of f is the value of f at 0 or f at 0. Okay, so to find, sub in x equals 0 and then solve for y. So opposite of this one. Okay, sub in x equals 0. So our coordinate will have this x equals 0 and then some number y. Okay, so if you think about subbing in x equals 0, again, these are the x values here. So if this is a 0, what we're doing is we're looking at how many units away from this x-axis, and this will land on the y-axis. And that's why it's called the y-intercept. Okay, so let's start this. Example 1, determine the intercepts in the graph below. So let's just name these x-intercept, and then we're going to go y-intercept. Okay, the x-intercepts, let's read the graph from left to right. So let's go smallest, -3. So you can either present these as x equals -3 or -3 comma 0. Then locate the next one, which is 1. So 1 comma 0. And then locate the next one, which is 4. So either comma 4 or 4 comma 0. Then we have the y-intercept. So go up and down the y-axis and locate the y-intercept. It's at -3. So we can say y equals -3, or we can write 0, comma, -3. All right, determine the x-intercepts for this function here algebraically. So let's write this out. F at x, and I always rewrite these, x cubed minus 3x squared minus 4x plus 12. Okay, so there are 4 terms here. This is not going to happen in like the second, third units, but for now, this is factor by grouping. So because there are 4 terms, we want to group the first 2, group the second 2, and then what we can do is we can do common factoring 3 times. So I'm going to divide the first 2 terms by x squared, right? Greatest common factor comes in front, and then we have x minus 3 left over. The second 2 terms divide by -4. So the -4, which is the greatest common factor, comes out front, and then we're given x minus 3 again. So we've done factor by grouping twice, and we have to do it one more time, but this time with these 2 terms. So let's divide by x minus 3. So we have x minus 3. Those cancel out. We're left with x squared. Those cancel out. We're left with negative 4. Okay, this x squared minus 4 is a difference of squares. So we'll bring down the x minus 3. And this factors to x plus 2, x minus 2. So as a reminder, and this is going to come up as well, so I'm just going to like rewrite this just so I have a little bit more room. So now we have f at x in factored form, x minus 3, x plus 2, x minus 2. Okay, so from above, when we're looking for x-intercepts, so let's just underline this first, x-intercepts, we'll just put a title. What we're doing is we're subbing in y equals 0. Okay, this is the formal way of doing this. So let's change color. In other words, we have 0 equals x minus 3, x plus 2, x minus 2. Okay, so one of three things has to happen in order for this entire side to equal 0. Either x minus 3 has to equal 0. So this is one situation. X minus 2 has to equal 0. Or sorry, x plus 2, my mistake. And then x minus 2 has to equal 0. So one of these three conditions has to hold in order for this entire side to equal 0. There are three different situations where this side would actually equal 0. So let's rearrange. X equals 3, that's one x-intercept. X equals negative 2, that's another x-intercept. And x equals 2, that's another x-intercept. And that's it. Okay, in regards to the y-intercept, okay, let's talk about when x equals 0. So we can go ahead and sub in f at x equals 0. You can do this in expanded or factored form. So even in expanded, 0 cubed minus 3, 0 squared minus 4, 0 plus 12. If you think about it, 0 cubed goes away, it's 0. 0 times anything is 0. 0 times anything is 0. And we are left with the y-intercept of 12. Okay, function behavior, increase, decrease, and constant. So we read a graph in mathematics from left to right, just how we're reading the sentence, okay? The same way we read a book. So increasing, the reason why I put all of these arrows going to the right is again, because we read graphs to the right. So a function whose input, so if you substitute a number into that function and output values increase together, so what happens is f at A is less than f at B. This is like the proper notation for this. Whenever A is less than B, the graph rises from left to right. What that means, and I'm going to make up two numbers here. So let's do 2.5, okay? Which is here. And then let's just do 4, which is, let's just do here, okay? So let's read this again. So the function at A is less than the function at B whenever A is less than B. So 2.5 would be A, 4 would be B, and we would be rising to the right because this number or this point here in the function is obviously lower than this point here in the function. So that means it's increasing. Okay, decreasing is the exact same thing except for it's going down. So again, reading the graph to the right, a function whose output value decreases as the input value increases, right? So this time f at A is greater than f at B. And all this means when A is less than B, this just means like in order. Okay, and what this means is the graph falls from left to right. So let's do a quick example. Let's go negative 1.5. So we're going to go from here. Let's go to like 1. That's fine. Okay, so in order, A in this case would be negative 1.5. That is definitely less than 1, which is our B. So we are increasing, so we're moving to the right, but the value at A is greater than the value at B. Right? See how it goes down? Okay, and then constant, a function whose output value remains the same for any input value. So f at A equals f at B, and so on. So this is when the graph is horizontal. Okay, we do not have an example of that here, but let's just make an example. So say we have, this is going to be at 12, and this is going to be at, I don't know, 5.5. Okay, so say we're horizontal to this point. This is still going to be at 12, right? But then now it's going to be like, I don't know, 8. So because this point has the same y value as this point, the graph is horizontal. Okay, so let's consider the following function. So the function over here, y equals f at x, shown on the graph. Identify the following intervals. So where is this graph increasing? So we are increasing from, remember we look at the y's but quote in x's. So look at y values, quote in x values. Okay, so all the way up to here. So we are increasing from -8 to -4. I'm going to put that into interval notation. Also, at -8, there's a stop. So we're not actually increasing at the number -8. So you don't include it, it's open bracket. We don't actually increase at -4. There's actually technically right here, just for a split second, it's actually constant. Like it's a change in direction. Okay, so the other place that we're increasing is here. So we're increasing from 3 to 6. Okay, now let's talk about decreasing. So decreasing from -4 to -2. And that's it for that one. Okay, we're not decreasing anywhere else. And then we're going to be constant from -2, oops, should have done this in another color, to 3. Okay, the domain of the function, we go from -8, that's going to be our lowest x value, and we go all the way up to 6. So XER such that x is between the numbers of -8 and 6. If you choose interval notation, you can do closed brackets, like big square brackets, because it includes -8 and 6. Okay, for the y values, let's take a look. I'm changing color. The lowest point here is -4, and the highest point is 8. Okay, so y is between -4 and 8, and it includes both because these are all closed circles. Okay, in interval notation, you are going to see -4, 8. Okay, relative and absolute extrema. So as a function changes between intervals of increase to intervals of decrease, its graph will create many ups and downs. Okay, and of course this is vice versa. So interval of increase, and then we reach a max, then decrease. Okay, so it'll be like an up and a down. Points where a function reaches an upward or a downward position are known as relative or local maximum or minimum points. Okay, so in theory, what this means, we have a relative maximum at x equals k, so any value k, such that f at x is less than or equal to f at k. That means that we're going up during that interval. Okay, x is here and then k is here, and those are on the x-axis. Okay, for every x in some open interval around x equals k. Okay, all this means is no point nearby is larger. Oh, I'm sorry, I'm going to go over this one more time. F at x is less than or equal to f at k. Sorry, these are the y values. Okay, so the y that occurs at x and then the y that occurs at k. That means that k value would be the highest value. So in this one, we can like this b, we can like label that. Let's just label it k. This is going to be a maximum. And then this one's going to be a minimum. And let's talk about relative minimum. So the function f at x has a relative minimum at x equals k. So at some k value, if every single other y value around it, and remember, we quote these in x's, but we actually look at the y's. Okay, so some other y value, say going up and down this y-axis, is everything else is larger than f at k. So f at k has to be the smallest on some open interval around x equals k. So all this really means is like, so if we take a look at like this area here or this area here in regards to the relative max and mins, there are no values bigger or smaller. So relative max, there's no value bigger, and then relative min, there's no value smaller. Okay, so now when we talk about an absolute maximum and an absolute minimum, what this means is it's the exact same thing except for it's on every x in the domain. So we originally just had like some open intervals around that number, but now we're going to talk about every x in the domain. So this domain strikes me as we're going from A to E as the domain. So take a look at this entire graph. The absolute maximum is the very, very, very maximum point, the highest of all the points. And then an absolute minimum would be the lowest of all the points in the entire domain. And I want to throw this out there. An endpoint cannot be a relative max or min, but it can be an absolute max or min. Okay? And these max and mins, these absolute max and mins, so this absolute minimum, it is an endpoint, so it can't be relative because we don't know if it keeps going down, right? So, but this one here is both an absolute max and a relative max. So pretty much by default, like if it's absolute, then it's going to be relative as long as it continues to go, as long as it's not an endpoint. Okay, lots of new jargon here. Example 4, identify the following from the graph below. Is there a relative minimum? So minimum, this one's going to be a minimum, so -3, -8. This is also going to be a relative min, 4, 0. Okay, relative maximums, 2, 1. All right, so in regards to an absolute minimum, this one's easy. You look on the entire graph Where's the absolute minimum? Its name describes exactly what we're looking for. It's going to be -3, -8. And then the absolute maximum. This is a little bit different because the maximums here would be going to infinity. So since the graph approaches infinity in the y direction, there is no absolute max. And again, think of it as you can never actually reach infinity, so that max is just continuing. So when you think it's within reach, it's like psych, and it's out of reach again, okay, because it's infinity. Okay, let's talk about boundedness. A function f is bounded below if there's some number b that's less than or equal to every number in the range. Okay, so obviously when we're talking about like above and below, we're thinking immediately the y-axis, right? Above, below. Okay, so we're thinking range. So y values. Okay, any such number is the lower bound of f. Okay, an example of this is right here. So this is bounded below, but not from, like above. Okay, so it's bounded below. And a function is bounded above if there's some number b that is greater than or equal to every number in the range. So this would be b, right? And then this is bounded above where this would be b, because this number would be the very, very basically maximum, right? It's some number b that every single number in the range is less than, whereas this one's greater than. Okay, any such number is the upper bound of f. Okay, now a function f is bounded in general if it is bounded both above and below. So this one is bounded here below, here above. Okay, and then there is an example here. This is not bounded below and not bounded above. This continues on up forever and down forever. So this one's not bounded. Okay, concavity and inflection points. So here's an example of concave up. Okay, it goes like the concavity is going up, whereas concave down, the concavity is going down. Okay, so for concave up, the slope is increasing. What this means is this slope, and I'm just going to draw tangents, this slope could be like -10, and then this is like -8, and then we have -4, and then we have 0, and then we have 1, 2, 3, whatever the slopes may be. So the slope is increasing. -10 is the smallest number here, and the slope continuously increases. Concave down, on the other hand, the slope starts at like, let's go 5, and then there's 3, and there's 2, and there's 0, -1, -7, I don't know, -10. I'm just making it up. Okay, so concave down would be, we're going from the biggest number, which is 5, to the smallest number, which is -10. So that slope would be decreasing. Okay, concave up is shaped like a U, or part of a U. Concave down is shaped like an N, or part of an N. And when we talk about inflection points, this is a little bit more specific. An inflection point is a point where a curve changes from concave up to concave down, or vice versa. Okay, and we're going to learn more about this in calculus. So let's do a question. So example 5, use the graph of g at x to determine the intervals of increase. Okay, so this is kind of putting everything together. So an interval of increase is going to go from, this would be -3, -3 to 2, right? Because we're going up in y values. So -3 to 2. Then another interval of increase is going to go from 4 to infinity. And remember, these values, -3, 2, and 4, these values, like at that specific value, we are not increasing or decreasing. It's like this would be like a turnaround point. So instantaneously, it stops. So like instantaneously, we would have like a tangent where the slope is 0. Okay? Okay, intervals of decrease. -infinity to -3. 2 to 4. And that's it. Okay, concave up and concave down. So if we take a look at this graph, it's going to go up forever. So reading from left to right, this here would be concave up. And this would be the point, so at -1/2, -0.5, this would be the point that we would go from concave up to concave down. Okay, so concave up would be from -infinity to the point -1/2. The point of inflection would be -0.5, -3. So these here are intervals, this is a point. Okay, now going from -0.5 to a maximum and then down a little bit to this 3, that would be concave down. Okay, concave up and concave down are from inflection point to inflection point, or like infinity, -infinity to an inflection point. So this is concave down. So it's going to go on the interval -1/2 to 3. Then from 3 all the way to infinity would be concave up. Okay, and then that point 3, 1 is also right here an inflection point. Okay, symmetry, odd and even and odd functions. So the terms even and odd describe the symmetry that exists for a graph of a function. So we're going to get more into this, and we're going to get into this algebraically. So for an even function, there's actually an equation. So if we were to substitute in -x for every single x value, it should pump out the same equation as the original function. That's what that's saying to us. Okay, and what this means is the graph is symmetric about the y-axis. So if you remember, I'm going to just take what is it called? A quadratic. I'm going to take half a quadratic though. Okay, so if we had this half of a quadratic, if you remember back to grade 11, if we put this negative on the x, what that is that is a horizontal, let's just actually put in general a reflection in the y-axis. That's what that is. So since this is the y-axis, we should be able to take the equation for this function, well, like the whole parabola, and we should be able to reflect it in the y-axis, and then this part of the parabola reflect that in the y-axis, which would go over there, and it should be symmetric. So the graph is symmetric about the y-axis, and then we can also do a quick check. All of the exponents on all of the terms need to be even in order for it to be an even function. That is not the only criteria, but that is a quick check to even approach the question, okay? Whereas an odd function is symmetric on the origin. Okay, so it's rotational symmetry. So in regards to the equation, this here would be reflection in the y-axis. This here would be reflection in the x-axis. So that what that would do for us is it would take our function that looks like this, reflected in the y-axis, so now it looks like this, reflected in the x-axis, so now it looks like this. Okay? And likewise, take this, reflect it, take this, reflect it, and now we get the same, like the exact same equation, the exact same graph. So this graph is definitely symmetric about the origin being 0, 0. Okay, again, a quick check to see if we should approach this way is to check that all of the exponents on the terms are odd. Okay, if they all are odd, it doesn't mean that it's an odd function, but it means that you can go ahead and algebraically check after. Okay, and then just note, if these two do not satisfy, then it's just, the function is just simply neither even or odd. Okay, it doesn't specifically have to be one of these. It doesn't have to have symmetry. Okay, so let's take a look. Determine whether the following functions are even, odd, or neither. So in A, I feel as though that this is going to be odd because it has rotational symmetry. Okay, I feel like this is going to rotate here, this is going to rotate here. Okay. For B, I feel like this is going to be even because this is like mirrored, right? So this is symmetric about the y-axis. And about is just like the way we say it in math. Okay, now C. C looks symmetric, like it looks like it has rotational symmetry around this point here. So it looks like you could rotate that and rotate that. And you definitely could. The issue is this is neither even nor odd because this would have to be at the origin. It's specifically rotational symmetry about the origin. So this is neither even or odd. Okay, for D, let's take a look. F at x equals 2x cubed minus x, and that's obviously to the exponent 1. So just by assessing the exponents, all of them are odd. So let's check if it is odd, okay? So f at negative x equals negative f at x. So this is how we do this. We're going to rewrite f at x, but instead of writing x, we're going to write negative x in a bracket. So 2 negative x cubed minus negative x. And then equals negative 2x. So this is going to be negative, and then we're going to write f at x all together. So 2x cubed minus x. And now all we do is simplify. So negative x cubed is still going to be, so this is going to be 2 times negative x cubed, right? Because that, we're really assessing whether like the positives or the negatives are changing, okay? And then negative x would be plus x, and we're going to distribute that in, negative 2x cubed plus x. And then I'm going to simplify this, so I get negative 2x cubed plus x equals negative 2x cubed plus x. This works, absolutely. Therefore, this is an odd function. Okay, moving on to E. So we have f at x equals x cubed minus 3. So here's the thing. We want to check whether the exponents on every term are even or odd. So this essentially would be x to the 0 because it would cancel out to like 1, right? So essentially this is neither even or odd. Okay, these clearly don't have even exponents, and although the x cubed has an odd exponent, this term -3, there's a constant, so therefore it's not symmetric about the origin. So this one's just simply neither even or odd. Okay, last topic, continuity. So continuity is a key concept for analyzed function behavior. Graphically, a function is continuous at a point if the graph does not like come apart at that point. So what this means is that like you can put your pencil down and you can draw this entire graph without lifting your pencil. Okay, you can draw this entire graph without lifting your pencil. This one too, and then this one too. Okay, there are different types of discontinuity, and that will be discussed in the course and then today as well. So a continuous function is a function whose graphs have no breaks or holes in it. Okay, a discontinuous function is a function whose graph either has a break, a hole, an asymptote, anything that disrupts the graph. Okay, so there is something called a removable discontinuity. In other words, it's called a hole. Okay, we're going to touch on this. This is where a point where the function is undefined and it's represented by an open circle. So we could have, oh, continuous, 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 continuous. Oh, there's a discontinuity. There's a hole. Then it continues. Despite it being continuous everywhere else, as soon as there's a hole, done, it's discontinuous. Okay, because the function here is not defined at x equals 2. That makes it discontinuous. Now we're going to be talking about piecewise functions, and there's something called jump discontinuity, and that's when there's a break in the function. Okay, so the values on the left of the graph do not equal the values on the right, and the function jumps to another function. Okay, so this is an example. So I can start here. Remember, we read graphs from left to right. Continuous, 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 and then we stop. I have to jump up to here and then go continuous, continuous, continuous. But because there's this jump, because there's this break, there is a discontinuity at x equals 3. Okay, and then there's infinite discontinuity, and this occurs when there is an asymptote. So a line that a graph approaches without touching. We've seen this before. So I'm going to just give the example of like there's a vertical break along x equals a. So again, the graph starts here. We continue, continue, but it goes down forever. Then there is a vertical asymptote, and we have to jump up here to infinity and come back down. Okay, the function here is not defined at x equals 3, making it discontinuous.